In this video, we'll be going through question 14 from the 2017 HSC Mathematics Extension 1 exam. So, part A. Prove by mathematical induction that 8 to the 2n plus 1 plus 6 to the 2n minus 1 is divisible by 7 for any integer n greater than or equal to 1. Okay, so here we have a math induction question. The first step is to prove the base case. So we're proving for n greater than or equal to 1. So the first value of n is n equal to 1. So that means our base case is when n is equal to 1. So subbing that in, we get 8 to the 2 times 1 plus 1 plus 6 to the 2 times 1 minus 1, which is equal to 8 cubed plus 6. 8 cubed is 512 plus 6, which is 518. And you can obviously just check on your calculator if that's divisible by 7, and you'll see that it is. It's actually equal to 7 times 74. Okay, and so therefore, we've proven that for n is equal to 1, this expression is divisible by 7. So therefore, base case is true. Cool. Now, the next thing we need to do is make our inductive hypothesis. So we need to assume that this is true for n equals k. Okay, and k has to be an integer greater than or equal to 1. Okay, obviously it has to satisfy the condition for n. So we assume that it's true for n equals k. So what does that mean? That means that we have to assume that this expression, where now we have n equal to k, so 8 to the power 2k plus 1 plus 6 to the power 2k minus 1, we have to assume that that's divisible by 7. And what does it mean to be divisible by 7? That means it's equal to 7 multiplied by some integer, and we're going to call that integer m. Okay, it's just a constant, so m is some integer. Okay, that's a symbol for saying m belongs to the set of integers. Okay, and what I'm going to actually do is I'm going to rewrite this in a slightly different way. I'm just going to move this 6 term to the other side. So it's going to be 8 to the 2k plus 1 equals 7m minus 6 to the 2k minus 1. And you'll see why in a minute. Okay, so I want to assume this. This is my inductive hypothesis. Now I have to prove it for n equals k plus 1. So now I have to prove that the statement is true for n equals k plus 1. So in other words, what do I have to prove? I need to prove that 8 to the power 2 times, now we're subbing in k plus 1 for n. So wherever I see an n, I have to put a k plus 1 plus 6 times 2 brackets k plus 1 minus 1. I want to prove that this is divisible by 7, which means that it has to be equal to 7 times some integer, and it's probably some other integer, so I'm going to call it n, where n is an integer. Okay, this is what I want to prove. Okay, so how do we go about this? Well, let's firstly move this up a bit. Let's consider the the left-hand side of what I'm trying to prove. So consider 8 to the 2 times k plus 1 plus 1 plus 6 to the power 2 times k plus 1 minus 1. Okay, let's do a little bit of manipulation with this. We want to try to involve our inductive hypothesis, so I'm going to call that star. Okay, that's our inductive hypothesis. We have to somehow involve that in this step. Now I've moved this the 6 over to the other side because I want to try to substitute 8 to the power 2k plus 1 in. So at the moment I have 8 to the, if I expand the brackets out in the powers, I have 8 to the 2k plus 2 plus 1, which means it's plus 3, plus 6 to the power 2k plus 2 minus 1. So that's 2k plus 1. 2 minus 1 is plus 1. Now, I still don't have 8 to the 2k plus 1, but I can see that if I do a little bit of factoring here, or using our exponent laws, we can make this 8 to the 2k plus 1 times 8 squared. okay, because we would just add our powers and we would get 8 to the 2k plus 3. So this works quite well. And then plus 6 to the 2k plus 1. Now I can use my inductive hypothesis, or the start equation. I can sub that in here. So I have 7m minus 6 to the 2k minus 1 times 8 squared, which is just 64, plus 6 to the 2k plus 1. And here I should say using the inductive hypothesis, or I'm just going to write star for this thing here. Okay, so we've used our inductive hypothesis there. Now let's expand out a little bit. This is equal to 7 times m times 64 minus 64 times 6 to the 2k minus 1 plus 6 to the 2k plus 1. Okay, how can I somehow look at these two terms here and join them together? Well, just like we factored out an 8 squared in a couple of lines above, I'm going to factor out a 6 squared from 6 to the 2k plus 1. And the reason I do that is because now I'll be left with 6 squared times 6 to the 2k minus 1. And both of these two terms will have a 2k minus 1 as the power of 6. So here I have 64 times 6 to the 2k minus 1 plus 6 squared times 6 to the 2k minus 1. So this is 7, and you'll see that I'm writing it as 7m times 64. Actually, I should put brackets around these, just because you'll see why I'm doing that in a moment. M times 64 minus, now let's factor out with a positive. So positive 6 to the 2k minus 1. If we factor that out, we'll be left with 6 squared, which is 36, minus 64. So I have 7 times 64m plus 6 to the 2k minus 1. Now 36 minus 64 is negative 28. Okay, and now what am I trying to do? I'm trying to show that this thing here is divisible by 7. In other words, it's equal to 7 times an integer, which is why I haven't actually multiplied 7 by 64, because 7's already factored out. But somehow I need to pull a 7 out of the second term, which is not too hard because we have 28, and we know 28 is divisible by 7. It's just 7 times 4. So this is going to be 7 times 64m, plus I can factor out a 7 here, and that'll leave me with negative 4 from the 28 times this 6 to the 2k minus 1. Now let's have a look. We have this term here. This is an integer, and the reason it's an integer is because m is an integer. We assume that in our inductive hypothesis right here. M is an integer, so we've already assumed that. 64 times an integer is going to be an integer. So this thing is an integer. We also have negative 4, another integer, multiplied by some power of 6, which is an integer. So this whole thing here is an integer as well. So I'm going to have 7 into 64m. Actually, that would be a minus 4 times 6 to the 2k minus 1. But we don't really care what's inside this bracket. We just care that it's an integer, which it is. Okay, so it's 7 times some integer, we'll call it n. Okay, where n is an integer and n is equal to 64m minus 4 times 6 to the 2k minus 1. Okay, and so therefore it's true for n equals k plus 1, but only if n equals k is true. Okay, and so then you can write the statement that you need to write saying, therefore the whole thing is true by math induction. And that's the end of the question. Part B. Let p, 2p, p squared be a point on the parabola x squared equals 4y. The tangent to the parabola at p meets the parabola x squared equals minus 4ay, where a is greater than 0, at q and r. Let m be the midpoint of qr. And then we're given this diagram showing that information. And part I says, show that the x coordinates of r and q satisfy x squared plus 4apx minus 4ap squared equals 0. Okay, so we need to find some information about the x coordinates of r and q. We need to show that they satisfy that equation. Now, what are r and q? R and q are the points where the parabola x squared equals minus 4ay intersects with the tangent at P. So that means we need to solve those simultaneously. Now, we don't know what the equation for the tangent is just yet, but we do know the equation of the parabola. That's going to be x squared equals minus 4ay. So we can call that equation 1. Now we need to work out the equation of that tangent at P. Now, that tangent is tangent to the parabola x squared equals 4y. So we're dealing with x squared equals positive 4y. We can divide by 4, and now we can differentiate in order to find the gradient at the point P. So dy on dx is going to be 2x divided by 4, which is going to be x on 2. And at the point P, which is 2p comma p squared, we have that dy on dx is going to be 2p divided by 2, which is just p. So that's the gradient of that tangent. Now, to find the equation of the line, of the tangent itself, we're going to use the point gradient formula, which is y minus y1. y1 is going to be p squared, equals m, which is p, x minus x1, which is 2p. Okay, so rearranging this will give us px minus p squared. Y equals px minus p squared. And this equation, equation 2, is the tangent of the parabola at the point P. So we can say this is just the tangent at P. It's good to write it so we don't forget. Okay, so I need to solve equations 1 and 2 simultaneously. So let's do that. Let's substitute 2 into 1. So subbing 2 into 1 gives us x squared equals minus 4a into px minus p squared. Expanding gives minus 4apx plus 4ap squared. And moving everything over to the left-hand side gives us x squared equals, let's get rid of that. There we go. X squared plus 4apx minus 4ap squared equals 0. And that is what we wanted to show. Okay, part 2. Show that the coordinates of m are minus 2ap, comma, minus p squared times 2a plus 1. Okay, so what was p? P was the midpoint of q and r. Now, we don't know what the coordinates of q and r actually are. However, we do know that the x coordinates of q and r satisfy this equation, which I'm going to call star. Okay, they satisfy this starred equation. Now, to find m, let's actually work out what m is. Since m is the midpoint of q and r, it's going to be the x coordinate of q plus the x coordinate of r divided by 2, comma, the y coordinate of q plus the y coordinate of r divided by 2. Okay, so this is just by the definition of a midpoint. Here's just the midpoint formula. For any 2 points, you can find the midpoint using that formula there. Now, why does that help us? Well, we'll actually be able to work out the x coordinate of m, and we're going to use the start equation to do that. We know that xq, or x sub q, and x sub r are solutions or roots of the start equation. Okay, so let's write that down. I'm going to write it in blue. xq and xr are the roots of our start equation. So why is that actually helpful? Because we know that we can work out the sum of roots of a quadratic. Okay, so that means that xq plus xr should be equal to minus b on a. So that's going to be minus 4ap divided by 1, which is minus 4ap, obviously. Okay, so therefore, the x coordinate of m is going to be xq plus xr on 2. Let's write that again, xq plus xr over 2. But what's xq plus xr? Well, we just worked that out in the line above. That's minus 4ap divided by 2, which is minus 2ap. Great, so we now have the x-coordinate of m. How can we work out the y-coordinate of m? We don't have any information about the y-coordinates of q and r, so we can't use a similar thing to what we did for x. But we do know that m lies on the tangent, okay, the tangent to p, and that was given by equation 2. So we can substitute xm equal to minus 2ap into equation 2. And that will give us y of m is equal to p times x of m, which is negative 2ap, minus p squared. So that's going to be minus 2ap squared minus p squared. And we can factor out a negative p squared, leaving 2a plus 1. Okay, and so therefore, m is going to be the x-coordinate, which was minus 2ap, comma the y-coordinate, minus p squared into 2a plus 1. Okay, and we've proven what we wanted to prove. Now for part 3. Find the value of a so that the point m always lies on the parabola x squared equals minus 4y. Alright, so here's our equation for the parabola x squared equals 4y, and this point m has to always satisfy that equation. That means that the x-coordinates and the y-coordinates of m should satisfy this equation. We should be able to substitute it in and it should be fine. So let's do that. Let's substitute everything in. So the x-coordinate gets squared, and that's equal to 4 times the y-coordinate, minus p squared, 2a plus 1. Okay, let's simplify everything here. That's going to be 4a squared p squared equals minus 4p squared times 2a plus 1. We can cancel a p squared and a p squared. We can cancel a 4 and a 4. That gives us a squared equals minus 2a plus 1. Bringing that over to the left-hand side gives us a squared plus 2a plus 1 equals 0. Now this here we can recognize as a perfect square. That's going to be a plus 1 all squared equals 0, and so a is actually going to be equal to negative 1. So when a is equal to negative 1, the point P always lies on the parabola. Okay, and that's the end of question B, or part B. Part C. The concentration of a drug in a body is f of t, where t is the time in hours after the drug is taken. Initially, the concentration of the drug is 0. The rate of change of concentration of the drug is given by f prime of t, or f dash t, equals 50 e to the negative 0.5 t minus 0.4 f of t. And the first part is, by differentiating the product f of t times e to the 0.4 t, show that d on dt of f of t times e to the 0.4 t is equal to 50 times e to the negative 0.1 t. Okay, so there's a lot that I just read out there. What's the main information? We know that the concentration of the drug is initially 0. That means that f of 0, so that means initially, is equal to 0. Cool, that's first bit of information. We're also given that f dash of t was equal to 50 e to the negative 0.5 t, that's a 5, and then minus 0.4 f of t. Okay, that was another bit of information. And then the first part says to differentiate that product. So let's do that. D on dt of f of t times e to the 0.4 t. So here we have something times something else, and we want to differentiate that. So that means we're going to use the product rule. So we differentiate the first. Now the derivative of f of t is just f dash of t, and we leave the second, plus we leave the first, f of t, and now we differentiate the second. So that'll be 0.4 e to the 0.4 t. Okay, now we know what f dash of t is. We're given that in the question. So we can substitute that in. So that means this is going to be 50 e to the negative 0.5t minus 0.4 f of t, and all that will be multiplied by e to the positive 0.4t, and then we also have this plus f of t times 0.4 times e to the negative or to the positive 0.4t. Now we can distribute in the first term, we can distribute out through the brackets, and we'll get the following: 50 e to the negative 0.5t times e to the 0.4t minus 0.4 f of t e to the 0.4t. And then here we have, I can bring the 0.4 out the front, 0.4 f of t e to the 0.4t. And you'll see that this here cancels with that there. All right, and we're left with this term. Now we can combine these two exponential terms. We just add the power, and that will give us negative 0.5 plus 0.4, which is negative 0.1t. And that is what we wanted to prove. So the second part says, hence or otherwise, show that f of t equals 500 times e to the negative 0.4t minus e to the negative 0.5t. Okay, so it says hence or otherwise, which suggests that we're probably going to use the information that we just obtained in the previous part. So let's just rewrite what we worked out. We proved that the derivative of f of t e to the 0.4t was equal to 50 e to the negative 0.1t. Now we want to find an expression for f of t, and I can see that I have an f of t here, but it's kind of stuck with that derivative there. So we want to try to eliminate the derivative. How do we eliminate a derivative? Well, we do the opposite operation, the inverse operation, which is to integrate. So we're going to integrate both sides here. So the integral of this thing, dt of f of t e to the 0.4t dt, is going to be equal to the integral of 50e to the negative 0.1t dt. Awesome. Now let's integrate that. Integral and derivative cancel, so I'm just left with f of t e to the 0.4t. And on the right hand side, it's going to be 50 e to the negative 0.1t, and we divide by the coefficient of t in the power, which is negative 0.1. And of course, we can't forget our plus c. Let's just simplify that a little bit. That'll actually become minus 500 e to the negative 0.1t plus c. So that's f of t e to the positive 0.4t. Okay, now we also had given in the question that initially the concentration was equal to 0. So that was the first thing we wrote down. That was f of 0 is equal to 0, and we used that initial condition to help us find our constant c. So if I substitute that in, this is what I'll get. I'll get 0 times e to the 0.4t, which is just 0, equals negative 500 e to the 0 plus c. So this is actually just equal to negative 500, and so c is equal to positive 500. So that means f of t times e to the 0.4t equals minus 500 e to the negative 0.1t plus 500. Now I just want f of t by itself, so I'm going to divide by e to the 0.4t, and that'll give me minus 500. When I divide, I subtract my powers, so that means it's going to be minus 0.1t minus 0.4t, which would be minus 0.5t. And this one here is going to be 500. The power is 0, so when I subtract 0.4t from 0, I get negative 0.4t. Okay, and I can just factor out a 500. And then I can write the positive term first, which gives us, that should be an e there, which gives us e to the negative 0.4t minus e to the negative 0.5t. Okay, and that is also what I wanted to prove. So that's part 2 done. Part 3 says, the concentration of the drug increases to a maximum. For what value of t does this maximum occur? Now, in part 2, we proved this expression for f of t, and we're trying to find a maximum. Okay, and a maximum, when does a maximum occur? A maximum or a minimum occurs when the first derivative is equal to 0. So that means f dash of t is equal to 0. So we want to differentiate this and then solve it equal to 0. Now, our derivative is going to be the following. 500 times negative 0.4 e to the negative 0.4 t. This will become negative 1 times negative 0.5, so that'll be positive 0.5 e to the negative 0.5 t. Now we want to solve that equal to 0. So that means 0 equals 500 into negative 0.4 e to the negative 0.4 t plus 0.5 e to the negative 0.5 t. Now I can divide both sides by 500. The left-hand side will obviously stay 0. This 500 will cancel. And I'm going to move this negative term to the left-hand side. So I'm going to get positive 0.4 e to the negative 0.4 t is equal to 0.5 e to the negative 0.5 t. Now here I'm going to divide both sides by 0.4 and both sides by e to the negative 0.5 t. So when I do that, I'll get e to the negative 0.4 t divided by, let's write it, 0.4 t divided by e to the negative 0.5 t. And again, dividing by 0.4 on both sides, I get 0.5 on 0.4. The left-hand side, I just subtract the powers. That'll end up with, or it'll end up as 0.1 times t in the power. And here I'm just left with 5 on 4. I can log both sides. 0.1 t equals the log of 5 on 4. And then I divide by 0.1, which is equivalent to timesing by 10, and I'm left with log of, or 10 times the log of 5 on 4. And what were the units? Doesn't say, it does say. The units were hours. So the time it takes is 10 times log of 5 on 4 hours until it reaches its maximum. Okay, and that's the end of that question and the end of the whole paper.